Hello, my name is Claire Horn, and I am a concurrent marine biology student here at HPU. Today, I'll be presenting my Capstone project, establishing pre-restoration baseline of coral health in Maunalua Bay. Does water temperature variability mediate the balance of coral and algae? Coral reef ecosystems are crucial in ocean health. These sessile populations provide numerous benefits to other reef-dependent species, as well as our ocean biodiversity as a whole. At this point in time, coral reef ecosystems are experiencing bleaching events that significantly alter their health and presence on a variable substrate. As coral cover declines, algae begin to take over and dominate the reef habitat. Here on Oahu and Maunalua Bay, we are experiencing these effects. Our vulnerable endemic species have declined, coral health has diminished, algal cover is increasing, water quality has worsened, and cultural connection has been set aside. The Kalua'ua'iha'i fish pond connected to Maunalua Bay is beginning a major restoration project to reconnect the natural waterways between the land and the sea. Similar fish pond restoration projects like the He'a fish pond in Kaneohe have shown significant coral recovery since restoration began. When concerning coral health, even the slightest thermal variation could have significant effects, and as our oceans continue to warm, these relationships are increasingly important to understand. This study aims to explore the relationship between microclimates and coral and algae cover before restoration. I explicitly looked at the average daily microclimate temperature ranges and their effects on coral and algal percentages in Maunalua Bay. I predicted that coral percentages would decrease with higher microclimate temperature ranges if influenced by warming events, or vice versa, coral percentages would increase with higher microclimate temperature ranges if influenced by cooling events. To test this, we deployed 36 hobo pendant temperature loggers on a 97,000 meter squared section of Maunalua Bay and took photos of a 1 meter quadrat surrounding each logger for substrate analysis. We recovered the temperature loggers from the coordinates taken during deployment, and only 18 of the 36 loggers were recovered, which are shown here in Figure 1. Each recovered logger was calibrated and time corrected for a total of 49 days. A total of 4 linear regression tests were conducted to see if the microclimate temperature ranges were either warming or cooling events. We set the regression significance to 0.05 to determine if the range was dependent on the average daily microclimate maximum or the average daily microclimate minimum. To test the dependency of coral and algal cover on the microclimate temperature ranges, 2 more regression analyses were conducted from the coral and algal abundance data to the respective microclimate temperature ranges. First, we needed to identify if the microclimate ranges were warming or cooling events. Based on the statistically significant values shown in Table 1 as well as displayed in Figure 2, both are significant, but we can see that the regression of the range dependent on the maximum has a much lower p-value than the range dependent on the minimum. From this test, we can assume microclimate temperature ranges are significantly dependent on the average daily maximum, and we can refer to them as warming events. After noting the microclimate ranges as warming events, the analytical results of the coral and algal cover dependent on the microclimate ranges are shown by the values in Table 2 or are displayed in Figure 3. Only the coral regression analysis was significant with an alpha value of 0.05. This statistically significant value implies that coral cover decreases when subject to warming events. When describing the relationship of coral cover dependency on the microclimate temperature ranges, many previous studies have presented similar results. Not only this, but coral species studied in Hawaii follow similar temperature threshold trends as the ones shown in Figure 3. We were unable to produce significance in the relationship between algal cover and microclimate temperature ranges. There are more algal species than coral species present in Maunalua Bay, and variation in specific thermal preferences are much larger for algae than for coral as well. We know that algal cover increases with water temperature, but the species' thermal preferences within our survey area may have been too large to notice within our sample size. The regression trend line seems to be increasing, but it is not statistically significant. Had we specified species during substrate analysis, more variability could have been accounted for. Overall, we were successful in completing the goals of this study: to create a baseline dataset for coral health in pre-restoration Maunalua Bay, and we have also gained a better understanding of coral and algal thermal variation on small spatial scales in effort to apply them to larger spatial scales. We experienced a few limitations, and some of you may have noticed that we went from 36 to 18 loggers during recovery. The limited logger recovery may have significantly altered our results, as having more loggers would have increased our sample size. Future studies could improve by curating a better logger recovery methodology, or by specifying the different substrate species present within the sample quadrat for more accurate results during microclimate range analysis. Thank you for joining me today. I appreciate your time, and here are some of my references. I look forward to answering your questions.